All right, so welcome to the second talk of the morning session, and it's part of a lecture series. And it's the first talk by Professor Henning Krause, and he's going to tell us about dualities for finite dimensional algebra.
Thank you very much. And of course, many thanks to the organizers for bringing all of us here to this beautiful place. And what I also appreciate a lot is the topics they have chosen, as in particular for the title, about dualities. So let me indicate why I find that appropriate. So the reference for this talk is actually a textbook, which I finished fairly recently, and I did a count. So the book has about 500 pages. So it's a textbook. It has about 500 pages, and now you can guess how many pages have, how often the word duality appears. I don't want you to guess now, but I tell you. So the word duality appears actually very often. So it's 134 times. And to give you a comparison, the word representation, the book is about representations, appears 226 times. So duality is really an essential feature in representation theory and homological algebra. Okay, so yeah, I'm a representation theorist. I do care about finite dimensional algebras, and this is what I want to explain today. So let me start with some examples. So suppose K is a field. And we have seen that already when G is a finite group, we can look at its path algebra, its group algebra, sorry. So we can look at KG, the group algebra. So this has been discussed a few times already. And because the group is finite, this algebra is finite dimensional because the group elements form a basis and the multiplication in the group provides you the multiplication of the algebra. So there's a similar sort of construction. Take a quiver. So if Q is a quiver, and the quiver is nothing but an oriented graph, and let's suppose without oriented cycles. Because when you now take its path algebra, then you get again a finite dimensional algebra because we don't have oriented cycles. I mean, we don't get infinitely many paths. There are only finitely many paths, and you take them as a basis, and the concatenation of paths gives you a multiplication. So we get the so-called path algebra. It turns out that homologically they are quite different. So a group algebra is an example of self-injective algebra. So KG is a so-called self-injective algebra. And one way to define this is, it means that projective and injective modules coincide. Injective modules coincide. Whereas quiver algebra is a hereditary algebra. So KQ is a hereditary algebra. So hereditary means that submodules of projective modules are again projective, therefore hereditary. And that means, so the global dimension is smaller or equal than 1. It's quite different. So the only sort of intersection of both classes are the semi-simple algebras, actually. Anyway, so these are the sort of important classes in representation theory which have been studied quite a lot. And one of the crucial tools is duality. And I want to tell you a little bit about this duality. So K is now any commutative ring. And you see matless duality generalizes the vector space duality for a field. Yeah? So therefore I keep that notation. So K is any commutative ring. And we take for sigma a representative set of simple K modules. And of course, simple K modules are parameterized by maximal ideals, but I look at them only up to isomorphism, simple K modules. And then what is matless duality? Well, I take the injective envelope of a direct sum of those. So the injective envelope. And this is nothing but a minimal injective cogenerator of the category of K modules. And then I can take the duality by just taking into E. Yeah, and because the ring is commutative, I get again from any K module, again a K module, which is its dual. So here are two important properties. So a little proposition. So there is a formula. Which relates sort of morphisms between a module and its dual. So this is for all. So there is no finiteness condition needed for all M K modules. But of course, one should be careful. I mean, one calls it duality, but it's not a duality in a strict categorical sense. I mean, a duality is a contravariant functor, which is an equivalence. It will not be an equivalence on the module category, and it's opposite. But if you restrict to finite length modules, it becomes an honest duality. Namely, module M is of finite length, so has a composition series, or equivalently, it is Artinian and Noetherian, if and only if it's dual, the M of finite length. Yeah, and then actually the natural map from the module to its double dual, sort of that's here is sort of an adjunction. So the functor D is sort of self-adjoint, yeah. And then the canonical, yeah, so the unit map is actually an isomorphism. So we get really an equivalence between the category of finite length modules via this duality. So an associative A algebra. A is called an Artin algebra. It's called called Artin algebra, or Artin K algebra to be precise, Artin K algebra, if A as a K module has finite lengths. If A as K module has finite lengths. That's a very nice finiteness condition. It generalizes finite dimensional algebras over a field. Yeah? So if you take for K in particular field, then an Artin algebra is nothing but a finite dimensional algebra. And if we denote by capital mod A, the category of all A modules, A right, no, what I meant is all right A modules. And I will actually drop the right. Yeah, so my convention is that I stick to right modules. If we denote here by capital mod the category of all right modules, then the finite length modules are somewhat distinguished. So M of finite length over A, if and only if M, so now I take a module M, if and only if M of finite length over K, because I can restrict, of course, to the ground ring K. And this happens if and only if M is finitely presented over K, over A, sorry. Yeah. So what the point is that finitely presented modules, which are somewhat natural to look at, agree with the finite length modules, which are also natural to look at. Yeah. And then for that reason, we really care about the small mod A. So this is a category of finitely presented A modules. And then matless duality provides an honest duality, meaning an equivalence of categories which is contravariant. Yeah? So here I take basically right modules. Here I take left modules. Because modules over the opposite ring are left modules. So this is now matless duality, but or Artin algebras. Okay. Now I want to talk actually about sort of a homological kind of duality, which is comes under the name Auslander-Reiten duality. So you will see my title was dualities. So I will talk about various dualities, but the basis for all this is matless duality. So now let's look at the Auslander-Reiten duality. A bit later, I will actually look at Serre duality. So there are various notions of duality. So let me denote by little proj A, the category of finitely generated projective A modules. And then, yeah, we have another duality. Namely, we can always hom into the ring. Yeah. This is, of course, also somewhat God-given duality. between the finitely generated projective modules on the right and on the left. And we want to use that as well. So there's also some notation for it. Now, see the best way to erase. Okay. Next time, I do a better job. So let me use the notation P star is this duality into the ring, or any finitely generated projective. Okay, so there's another duality, which is sort of derived from this one, namely, for a finite represented module, we have a finite presentation. I have a presentation right, with the PI finitely generated projective. I mean, this is the definition. And then I can take the dual of this map, and then I get a map from P0 star to P1 star, and I can take its co-kernel. So this is the transpose of M. This definition goes back to Auslander and Richter. So this is the transpose, and it actually provides a duality. Maybe I should mention it for any ring, actually. Another duality, sort of Auslander, Richter. I'm not using it. I mean, the point here is this sort of construction is not really unique, yeah, because such a presentation is not unique. Yeah, just two steps. A presentation meaning two finitely generated projective modules, and the module M is a co-kernel of that. Yeah, and now if I dualize this map here, yeah, I get a map sort of in the other direction, and I take its co-kernel. So my point here is that this construction cannot be unique, yeah, because I mean I can choose different presentations, yeah, and then the module here will also differ. But this happens only up to morphisms factoring through projectives. So the Auslander-Reiten, Auslander-Richter duality is actually one I pass to the stable category. I mean, this module is again finitely presented. So where this means, so this is a stable category. Stable category. And the stable category means I take as homomorphisms between two modules the home underline. I take the quotient, the quotient of the A module morphisms modulo those which factors through a projective module. Yeah, so these, they form a subgroup. Yeah, so they form a subgroup. I can take the quotient, and this becomes then a sort of an additive category, and we have this kind of equivalence. But I put it in bracket because I won't use it later. Yes, that's a transpose. Yes, exactly. The module M descend to the transpose of M. Yeah, thank you very much. Good point. So this is Auslander-Reiten. But my aim is rather to explain Auslander-Reiten duality. But it uses the transpose. Yeah, Auslander-Reiten duality, of course, refers to Maurice Auslander and Idun Reiten. They came up with that in the mid-1970s. So here's the theorem. Theorem U2 Auslander and Reiten. Namely, so for any module, so M is a finitely presented module, A an art in algebra. So for example, finite dimensional algebra. Then we have an isomorphism. Well, between the functors, I take the underline, take its dual. This is isomorphic to x1 of the dual of transpose of M. So what it means is we can actually compute X groups between finite dimensional modules using the dual of transpose construction. In particular, this dual of transpose gives us another equivalence, namely from the stable module category. To the injective stable category of A op. Oh, no, sorry, it's the same. Of course. Yeah, so the dual of it's actually an equivalence. It's an equivalence because I compose two dualities. Yeah, which takes a module to its dual of transpose, provides an equivalence between these categories. And this is what I meant when I said we can compute extension groups x1 using the dual of transpose, because any finite dimension module is of the form dual of transpose of a module. Yeah? So the overline is the obvious thing. If you define a tier modulo projectives, you define a tier modulo injectives. And this makes sense because sort of here, overline, is by definition modulo the subgroup of morphisms factoring through a projective. Injective, sorry. Yes. These are sometimes called stable homomorphism groups. Yeah? So the stable modulo projective. But it's a K module. It's a K module, and therefore I can use the Matless duality for K modules. So this is an isomorphism of K modules. As K is any commutative ring. A is arting K algebra, where K is any commutative ring. K is any commutative ring, so I have matless duality. Yes, I use now the matless duality over K, because HOM is just a K module, because A is not a commutative, not necessarily commutative. Yeah, so it's just a K module, and I can use sort of look at its K dual, so to say, matless dual, and that's the relation. Auslander-Reiten. Quite intriguing. Has very sort of many consequences, and in particular, there's a sort of Auslander-Reiten quiver, which sort of comes up naturally from this formula, but I'm not going into it. Are there more questions at this stage? Probably going too fast.
Hello, yeah. Is this duality some, like what sense is this duality in? Is this the monoidal category duality or just a contravariant functor?
For the category of A modules, we don't really have a good monoidal structure.
Right.
Because it's not assumed to be commutative ring. Yeah, so yeah.
By duality, you just mean any contravariant equivalence?
Well, I mean, duality, did I call it Auslander-Reiten duality? It's the Auslander-Reiten formula. I mean, it is actually a covariant equivalence, but it uses two dualities. Yeah, it uses the Auslander-Bridger duality, and it uses matless duality and combines both. Yeah, so in that sense, it is derived from duality.
Okay.
I hope I didn't call it Auslander-Reiten duality because. Yeah. Let's call it Auslander-Reiten theory. Well, yeah. There is some logic, as Shrikant points out, yeah, because there is actually later in lecture 2, lecture 3, we will see further incarnations of this that are sort of very close to local duality. Yeah? Yeah, thanks. These are good comments, actually. I was a bit careless, as you can see. So far about Auslander-Reiten, and now I want to pass to Serre duality. But actually, I start with a little discussion about derived categories. So whenever A is in a Abelian category, I want to denote by dB of A its derived category, bounded derived category. So bounded complexes of objects in A, where I sort of identify those which are quasi-isomorphic. It's a triangulated category. Let's look at an example where derived categories are really feature very nicely. This goes back to Bailinson. So we take the projective n space. So K a field. K is now a field. We take the projective n space. Projective n space. And we look at its derived category. And Bailinson gave a very nice description in terms of linear algebra. And this uses the notion of a tilting object, or the notion of a derived equivalence, this is what I'm going to explain now. So we look at the derived category, the bounded derived category of coherent sheaves on Pn. And there's a distinguished object, the so-called tilting object, where I take twists of the structure sheaf up to n. And now I can, this is a so-called tilting object. So what does it mean? Well, I look at the endomorphism algebra. So let me denote by Bn the endomorphism algebra of this object. Yeah, it's a finite dimensional algebra because the category of coherent sheaves has finite dimensional Hom spaces. So it's a finite dimensional algebra. K algebra, I should say. And I will give you later an explicit description. Or maybe I give it now, because it's given in terms of quivers and relations. Yeah, so you look at the so-called Bailinson quiver, which has n plus 1 vertices and between each pair of adjacent vertices, you have n plus 1 arrows, and I denote them by x0 up to xn. Okay, so we look at this quiver, and now we impose some relations on it. Yeah, so this is a finite quiver without oriented cycles, so the path algebra is a finite dimensional algebra, but we quotient out an ideal, and the ideal is just given by this relation xij equals xj xi for all I and j. So this is the explicit description of the Bailinson algebra, which is not so difficult if you know how to compute morphisms between the structure twists of the structure sheaf. So isomorphic to this path algebra modulus this ideal of relation. Yeah, and now if I take now the derived Hom functor, I get into the bounded derived category. Over this finite dimensional algebra. Yeah, I mean, this is what the endomorphism algebra of T is, the Bailinson algebra, and therefore we get into the derived category of the Bailinson algebra. And this is, yeah, the derived equivalence which Bailinson constructed. It is somewhat a beautiful connection because now you see that you can sort of translate problems from geometry into linear algebra. That was the way Bailinson was thinking. But we can now think as a sort of representation theorist, we can now think what it means, what can we learn from geometry? And there is, for example, the notion of Serre-duality. So next I want to talk about Serre-duality. Because we have Serre-duality for this category, and then by transport of structure, it of course sort of translates to a Serre functor on this side. So let me give you the right definition. So if C is any Hom finite K-linear category, meaning C is an additive category. The HOMs are K modules, and the composition is compatible with the K-linear action. So it's a K-linear category. So HOM XY is a K module of finite length for all objects X and Y in C. Yes, therefore HOM finite, I mean finite length. So I can apply again modulus duality. So K is a commutative ring, but for Bailinson it is a field. It's a field, yeah. I mean, for that definition, you can take any commutative ring. I'm giving you now the definition, but again, the interesting cases are those where K is a field. Let's see. So a self functor is an equivalence F together with natural isomorphisms with natural isomorphisms between the dual of HOM XY and HOM Y Fx. So for X, Y, any pair of objects in C. Yeah, so because the HOMs are K modules, I can apply the duality, and basically I ask, is this functor representable? Yes, it is representable by the object Fx. Yeah, so in that sense, the functor F is somewhat determined by these isomorphisms. Anyway, so this is a definition of a self functor. And if I have a smooth projective scheme, then the bounded derived category of coherent over projective scheme of a field K, then I have, well, thanks to cell, there is a self functor, and therefore we get also a self functor here. And I want now to ask if we have just a finite dimensional algebra. I mean, does there exist a self functor in general? This is not true. I mean, for a projective scheme, one needs to assume it is non-singular, and the sort of appropriate condition for finite dimensional algebras is that the homological dimension is finite. So here's a theorem due to Happel. So Dieter Happel was actually the first who studied, he's a representation, he passed away. He was a representation theorist, and he was the first who sort of took derived categories seriously and did some beautiful work. And here's one of his theorems. So an Artin K algebra. Yeah, K is any commutative ring. Then the bounded derived category of finitely presented modules over A admits a self functor if and only if the global dimension, global homological dimension of A is finite. Yeah, so in general, there will not be a self functor. But in those cases, we get, for example, here from the scheme, which is smooth, we get finite global dimension for the endomorphism algebra, and then there's a self functor. And one equivalent way of phrasing it is that if I look at the category of perfect complexes, so this is category of perfect complexes, this is actually equivalent to the bounded derived category. Yeah? Because every module, finitely presented module, has a finite resolution. By definition, if I assume finite global dimensions, then it is actually a perfect complex. Okay. Now you may wonder, what is the self functor? How does it look like? And there is actually an explicit description. Yeah. Because the self functor is determined by this formula here. Yeah? As I said, it's given by that formula, and the self functor equals the same as the so-called derived Nakayama functor. So what is a Nakayama functor? Well, that's something which comes sort of very naturally. Well, see, I mean, if I take A as an A module, this is a projective generator. And now we know that for the category of finitely presented modules, we have a duality. Matless duality gives us a duality for the category of finitely presented or finite length modules. And then a projective generator is turned into an injective generator. So dA, I mean, if I want to be very picky, I take the opposite algebra, take its dual, that will be again the right module. This is an injective generator. Okay, so therefore it makes sense to look at this functor. Now I view dA as a left A module, as right A module, and so this is functor. So this is the Nakayama functor. Why is it called Nakayama functor? Because, well, if the algebra is self-injective, then these will be isomorphic. Yeah? So A and dA will be isomorphic. But the indecomposable summons sort of get permuted. Yeah? So the indecomposable summons of A correspond to the simple modules. But if you have a group algebra, they correspond also to characters, and the characters are sort of getting permuted, and this is the so-called Nakayama permutation. Yeah? It's a Nakayama permutation which sort of Nakayama came up with or used, and this is sort of the categorical version of the Nakayama permutation for group algebras. Anyway, now let me go on. I mean, there's sort of a disappointment here because we have Serre duality only for algebras of finite global dimension. On the other hand, we do care about algebras of infinite global dimension. Yeah, for example, group algebras. Yeah, they are not covered by this result. Yeah, so I want to do something about that and want to tell you about Gorenstein algebras. Yeah, so you can derive that functor. So you derive it, so you take the left-derived functor. I guess the tensor functor is left exact, so you take the left-derived functor. And, well, in general, if you derive, you get a functor, say, from bounded below complexes to bounded below complexes. But if you assume finite global dimension, then this will restrict to a functor on the bounded derived categories. So this is the derived Nakayama functor. Derived Nakayama functor. And it provides an equivalence. Yeah, the Serre functor is actually an equivalence. It provides an equivalence if we assume that the global dimension is finite. Are there any further comments or questions? Yes, under that assumption, global dimension is finite. Yeah. Yeah. Mm-hmm. I think, yeah. I think the category, yeah. No, I mean, let's see, you see, I mean, on the abelian category, I mean, the home functor. No, I think the dual of the home functor is left exact, right? No, right exact. So the dual of a right exact functor is a left exact functor. Well, what happens? So therefore, so I mean, for the abelian category, you can expect a Serre functor. This is what I'm saying, except the category is semi-simple. Yeah, because the dual of a left exact functor is right exact, but this functor is again a left exact functor, and it can only be right exact if this is projective, right? So only if the category is semi-simple. For the abelian category, you can expect a Serre functor. Sorry, I really meant this. Yeah. So the fx is the representing object for this functor. Yes, yes. So this is that set of. Yeah. I hope I got that right. Yeah. Mm-hmm. Nonetheless, I mean, you see, I mean, the derived category is a triangulated category, and there's more symmetry, and therefore such Serre functors exist. But for an abelian category, one should not expect, except the category is semi-simple. Now let's move on to Gorenstein algebras. Okay, so now A is a two-sided two-sided Noetherian ring. So A is called Iwanaga-Gorenstein. If by definition, so the definition goes back to Iwanaga, but Gorenstein algebras Gorenstein rings were studied before in the commutative setting. Here, I don't assume the ring to be commutative. If the injective dimension of A as a right module is finite and the injective dimension of A as a left module is finite. Yeah? If I have this finite homological finiteness condition, one calls the ring Gorenstein. And if one has this, then actually both dimensions coincide, and this is the so-called Gorenstein dimension. Here are some examples. So if the global dimension of A is finite, then obviously A is Gorenstein. Actually, yeah. So this is Gorenstein algebras, generalized algebras of finite global dimension. But on the other hand, also, if A is self-injective, it also implies that A is Gorenstein. And this is sort of a nice feature that we generalize two classes of algebras which are fairly natural to consider. Here's another example how to construct sort of new algebras from old ones. So if A and B K algebras over field K, actually finite dimensional. Then if A, B are Gorenstein, then also their tensor product. Yeah, I can take the tensor product of both algebras over K. It is again a finite dimensional algebra. This is also Gorenstein. Yeah, okay. So I drop, good point. From now on, I drop this Iwanaga. Yeah. Yeah. So I just call them Gorenstein algebras. Mm-hmm. So one could say more about the connection to the notion of Gorenstein in the commutative setting, but maybe I leave that for the problem session. Here, yes. No, I mean, the self-injective algebras, for example, a group algebra, I gave you that. Yeah. Okay, in the commutative setting, yeah, self-injective is rare, yeah. Yes. Need to be Krull dimension 0, basically. Self-injective implies Krull dimension 0. So in that sense, it's rare, yeah. Mm-hmm. Mm-hmm. Yeah, only the Artin algebras are sort of interesting, yes. Mm-hmm. Yeah. Okay, I just wanted to give you the sort of nice formula here. There is this notion of Gorenstein dimension of A tensor B is the same as the Gorenstein dimension of A plus the Gorenstein dimension of B. And this is the Gorenstein dimension. Yeah, they coincide, and then one calls it the Gorenstein dimension, and that formula is sort of an explanation for this fact here. No, they are all, when they are finite, they are equal. Yeah. So, shall I write it? No. If both are finite, then they're equal. If both finite, then they are equal. Yeah, I mean, this is a sort of result due to Auslander-Sachs. Sachs was a student of Auslander. And then this term Gorenstein dimension makes sense. It's well defined. I want to give you an example. I mean, really explicit example, because sort of what is the smallest interesting algebra of finite global dimension? So here we take this algebra here, upper triangular matrices. So this is the smallest, it's non-commutative. It is actually the path algebra of the quiver. It's a path algebra of this quiver. So it is a hereditary algebra. Now, global dimension 1. Now I take the smallest interesting self-injective algebra, which is that? I take for B, which is not semi-simple. Yeah, it's this sort of group algebra of the cyclic group. Now I take the tensor product. So this is hereditary, this is self-injective. So the Gorenstein dimension, this has Gorenstein dimension 1, because the Gorenstein dimensions add up. So let me get more space. So the Gorenstein, in this case, the Gorenstein dimension of A tensor B equals 1, yeah, for this example here. And how does it look like? So we have actually these two generators here, T1 T2, and we have here a generator which I call A. Yeah. So we get a quiver, and we take relations T1 square equals 0 equals T2 square, and also A composed with T2 equals the same as T1 composed with A. Yeah? So if you in other words, if you compute the tensor algebra of those two, you get this quiver with these relations. Yeah? So that's it's a sort of a nice algebra of finite representation type. And it is fun sort of to compute. It's in decomposables, in decomposable representation. I think they are 9 indecomposable representations. Okay. Yeah, now I want to talk about the square, yeah. Ah, yeah, sorry. So now I want to get to the beautiful theory of Buchwald's, or Auslander-Buchwald's, actually the so-called Gorenstein approximations. So how do we sort of treat the category of modules over Gorenstein algebra? It admits a nice decomposition. So a module, suppose now A is Gorenstein or Iwanaga-Gorenstein. No? A module M is called Gorenstein projective. Gorenstein projective, sometimes also called maximal Cohn-Macaulay or maximal Cohn-Macaulay. If the extensions with A vanish for n greater than 0. Yeah, all higher extensions between M and A vanish. Maybe I want. No. So here's a theorem about the Auslander-Buchwald's approximations. Maurice Auslander and Ragnar Buchwald's. Yes, non-commutative. So they both insisted, I mean, Auslander, Buchwald's both insisted on this theory for non-commutative rings. Of course, they were inspired by commutative rings, but yeah, non-commutative. So let X be the category of Gorenstein projective A modules. So these are all the modules, as Shrikant points out, one should assume finitely presented. M Gorenstein projective. And Y, the category of modules, there's no extra notation for it, which have finite global dimension. The projective dimension of M is finite. And it turns out that they are somewhat orthogonal to each other and provide a decomposition of the module category. Then the pair X and Y is the so-called co-torsion pair. And of course, I will give you the definition. And if you look at the intersection of both classes, these are just the finitely generated projective modules. So module is in both classes only if it is finitely generated projective. So we can think of this as a decomposition. So what is the definition of a co-torsion pair? Yeah, it's a pair of two subcategories which are orthogonal with respect to all higher extension groups. So here's a definition. A and a B in category. For example, the category of finitely presented modules over A. So X, Y, full subcategories. Then we define sorry, not ready. So a full subcategory. Then I define C right orthogonal. All the objects say Y in A, so that X, N, X, comma Y vanishes for all X in C and N greater than 0. And dually, C left perp are all the objects X in A, so that X and XY vanishes for all Y in C and N greater than 0. Yeah, so I define sort of the perpendicular category with respect to higher extension groups. And then X, Y is a cotorsion pair. It's a cotorsion pair. If, yeah, the right orthogonal of X equals Y and the left orthogonal of X. No, sorry. And X is the left orthogonal of Y. And we're not done. It makes a difference, yes, yes. Yeah, I mean, sometimes they agree, but yeah, I mean, that definition also makes sense if you just stick to X1. But here I want to take all the extensions. And so I want actually additional condition for each object. There exist exact sequences of this form. And now you can guess what are the conditions on these objects X sub A and Y sub A with the condition that X sub A and X upper A are in the class X and Y sub A and Y upper A in the class Y. Yeah, and these are sometimes called approximations. So I take an arbitrary object and I take an approximation from the right sitting in X, and also to the left there's an approximation which sits in Y. Yeah, and this goes under the name Gorenstein approximation in this special situation. Because X is now, for the Gorenstein algebra, X is a category of Gorenstein projective modules. So definition. Yeah. So, yeah. So here is a definition for module. one calls the XA, it's Gorenstein approximation. And we use the notation GP of A. So this is a notation for the Gorenstein approximation. Okay, so this will be relevant now. Yeah, there's is a cotorsion pair with that property that the intersection of these two subcategories, the intersection, yeah, I mean, it makes sense, yeah, if you have sort of a decomposition, you're wondering what sort of is sitting in the intersection, yeah, in both classes, yeah, and only the projective ones, yeah, I mean, Y is the modules of finite projective dimension. The modules of finite projective dimension. And I call this a decomposition. A decomposition of the category of finitely presented modules. Yeah, so a decomposition means you have sort of these two subclasses which are perpendicular to each other, and the intersection is small. Yeah? Oh yeah. So X is sort of the right approximation. Yeah. Up to in the stable category, it becomes a functor. Yeah. I will get to that. Because now I want to talk about yeah. So here's the next lemma. So lemma. So A is again Gorenstein. We keep it for the rest. Then this category of Gorenstein projective modules is an so-called exact Frobenius category. So what does it mean? Is an category Frobenius who has enough, projectives and injectives, enough projectives and enough projective objects, enough injective objects, and they coincide. And if you look at the definition of Gorenstein projective, I mean, the definition is really made in such a way that A becomes an injective object, yeah? Because there are no extensions for a Gorenstein projective module, there are no extensions with A. Yeah? So A is in the module category a projective object, but in that subcategory it also becomes an injective object. And it turns out that the projectives and injective coincide. They are just the projective modules. With the category of projective modules are just the projective injective objects in this exact category. And because it is a Frobenius category, we can pass to its stable category, and it becomes a modulo projectives or modulo injectives. It doesn't make a difference. and it becomes a triangulated category. So corollary, the stable category. And by now, you know what I mean by underline. I mean, passing to morphisms which kill those which factor through projective is a triangulated category.
Excuse me?
Yeah?
In the definition of Gorenstein approximation,
Yes.
Is A getting overloaded, or do you mean A as a module over itself?
A is a finitely generated module. Ooh. Yeah, good point. Well, thank you. Yeah. Yeah, A is our algebra, of course, and yeah, here in that definition of a Rho-torsion pair, I use A in a different way. Sorry, but I think now it's I think fixed. Thank you very much. Good point. So we have triangulate. The stable category is a triangulated category with suspension taking an object X to, or module, to its inverse syzygy. And so exact sequences of the form, say, X to Y to Z in this category correspond to exact triangles of the form X to Y to Z to omega inverse of X. Hmm? Yes. Mm-hmm. Mm-hmm. Yeah. Hmm? No, I mean, these are just objects in the category of Gorenstein projectives. Yeah. Yeah. Mm-hmm. Oh, I have 10 more minutes. Hmm? Ah, sorry. Maybe then I'm sorry, I was. Can I get 1 more minute? Yeah. So the Buchweiz proves actually that if I take the inclusion into the bounded derived category and then quotient of the bounded derived category modulo the perfect complexes gives us an equivalence, of triangulated categories. So this is often called the singularity category. All of three discovered that. Singularity category and a corollary somehow this category has a self-functor, admits a self-functor. So that is my point. I mean, if the bounded derived category of modules does not have a self-functor in general, but if the algebra is Gorenstein, then the stable categories, the singularity categories, the stable category of Gorenstein projectives admits a self-functor, and that self-functor is actually given by the following assignment. We take a module M to omega inverse the Gorenstein projective approximations of the dual of transpose of X. Yeah, so the Auslander-Reiten dual of transpose, we do the Gorenstein approximation, we take its suspension, and then this will give us the self-functor. Okay, so I'm terribly sorry for getting over time. What I did today, I looked at finite dimensional algebras, looked at sort of the K-linear structure and used duality, mapless duality. Next time we will actually use higher sort of structure in the sense that we take the group cohomology for modules over group algebras and use sort of the action of the group cohomology on, so that acts sort of on the stable module category of a group algebra. And again, we can use duality. Thank you very much.
So are there any questions for the speaker?
Hmm? Which suspension? Ah, the inverse loop. Ah, very good point. Yeah, I didn't have the time. So if you have a module, a Gorenstein projective module, you know, I mean, the category has enough projectives. So you take a projective or injective, and then the co-kernel. Yeah. So this is the sort of opposite construction for a suspension, the Heller operator, where you take a projective cover. Mm-hmm.
Are there other questions? So I just had a question in the Bellinson's example of the graph,
Mm-hmm.
like how many vertices you had n+1, or like any two adjacent vertices at n arrows, x0 through xn, right?
Yeah.
But
I did not label them. Yeah. So I had. So this was number 1, 0, 1, and this is n.
okay.
And that makes sense because it was the endomorphism algebra of basically these n+1 twists of the structure sheaf, and each is sort of indecomposable. Yeah. So yeah. And the vertices correspond basically to the idempotents coming from these the endomorphism algebra, the identity maps from the twists of the structure sheaf. Yeah. I don't see an immediate relation. I mean, morally, of course, yes. Morally, yes. I mean, you try to decompose a category.
There is harm space also is involved.
Hmm?
Here you have only higher.
Yes, exactly. Yes. Yes, that's the point. Yes, yes. In a semi-orthogonal decomposition, yeah, that's the difference. Yeah. On the other hand, I mean, yeah, I mean, if you sort of, if you pass to sort of that stable category, it gets closer to a semi-orthogonal decomposition. Yeah. 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 Mm-hmm. And I mean, you see the relation also here. Yeah. I mean, you have sort of the modules of finite global dimension as sitting inside that category, and this is a quotient. Yeah, I mean, if you have a semi-orthogonal composition of a triangulated category, I mean, you have a 6 subcategory and you have a quotient in a sense, right? And here you see the same. Yeah? So you have that 6 subcategory, the modules of finite global dimension, and the quotient are the modules, the Gorenstein projectives. Yeah? So there is a parallel, of course. Yeah. Yeah, there's another question. John.
At the beginning, you were alluding to various sorts of duality, and you said this is a duality and this one isn't. Do we have a definition of what a duality is?
Well, there is a categorical definition. Yeah, a duality is a contravariant equivalence, and yeah. Well, maybe I don't have a good definition at that stage.
Okay, if there are no other questions, let's thank Henning once more.